During World War II, propeller designers faced many problems as they strove to satisfy the requirement for fighters with high-speed performance, short takeoff runs, and rapid rates of climb. The answers came quickly. Initially, the Spitfires and Hurricanes fixed-pitch propellers were replaced by two-pitch propellers. Fine pitch was selected to give a suitable angle of attack for takeoff and climb, then changed to coarse pitch for cruising and high speed. Though superior to fixed pitch, there was still a large sector of the speed range where the propeller was not operating efficiently. A further drawback to both fixed-pitch and two-pitch propellers is that because their rotational velocity is governed not only by the power setting of the engine, but also by the aircraft's speed, pilots must be careful not to over-rev engines in steep dives. This problem was eliminated in Spitfires and Hurricanes by converting their two-pitch propellers to variable pitch units shortly prior to the Battle of Britain. This also shortened takeoff runs, increased rates of climb, significantly improved maneuverability, and lifted their operational ceilings. The introduction of variable pitch enabled the propeller to work close to its maximum efficiency over a wider speed range. With a variable pitch propeller, a constant speed unit automatically adjusts the blade angle to maintain a constant loading on the engine. The selected propeller RPM remains the same, regardless of engine power variations and airspeed. However, a potential problem was created. If the engine failed, the rotational velocity would start to decrease, and the constant speed unit would reduce the blade angle to try to maintain the RPM until the blade reached the fine pitch stop. Now the relative airflow strikes the forward surface of the blade, creating a negative angle of attack and reversing the torque so that the propeller drives the engine. This is known as windmilling. The decrease in performance it causes will reduce the gliding range, and if the engine is damaged, continuing to turn it could cause it to seize or even catch fire. Improvements to the variable pitch propeller enabled it to be feathered by turning it into a position of zero torque to stop the engine turning and minimize the drag. A tactical landing. The bulk of a Hercules brought to a halt in about 750 meters, and the pilot wasn't trying too hard. Reverse thrust, a further development in pitch control, not only brought dramatic improvements in braking, it also enabled aircraft to be reversed using their own power, and made maneuvering on the ground far easier. Reverse thrust is produced by turning the blades past the flight fine pitch limit to create a relatively large negative angle of attack. But to return to World War II and another problem facing propeller designers. How to develop them to absorb the ever-increasing power outputs of the engines. Propellers must be able to absorb engine power. Otherwise they'll just spin faster to no effect. The answer is to increase the area of aerofoil surface. There are two ways of doing this. Firstly, the diameter can be increased. This enables an efficient high aspect ratio blade shape to be maintained, but increases the tip velocity, which is of critical importance, since compressibility effects at transonic and supersonic speeds greatly increase drag, which reduces the propeller's efficiency. Another way is to increase the propeller's solidity, which is the proportion of the propeller disc filled by the blades. But increasing the chord reduces the blade's aspect ratio and its efficiency. So designers opted to increase solidity by adding more blades. During late 1939, the Spitfire's two-bladed propeller was replaced with a three-bladed model. In 1942 came the Mark IX with its four-bladed propeller. And the final Spitfire Marks were equipped with five-bladed propellers, in common with many other fighters of the day, which was the maximum number that could be fitted to the hubs at that time. But when still more powerful engines were developed, the designer's solution was to use contra-rotating propellers. The diameter of the B-36's propellers was a massive 19 feet, because on load-carrying aircraft, larger propellers had to be used. But the stresses of their blade roots can be enormous, as much as 22 tons. Three principal stresses affect propellers, and centrifugal force causes two of them. The first is produced by the radial component, which tries to tear the blades from the hub, and the second by the tangential component, which tries to turn the blades to find the pitch. The centrifugal twisting moment. The third principal stress is generated by the total reaction, which tries to turn the blades in the opposite direction, the aerodynamic twisting moment, which reduces the effect of the centrifugal twisting. But if the propeller is windmilling, this aerodynamic twisting will be reversed. So at high speeds, the combined stresses could overwhelm the pitch-changing mechanism and make it impossible to feather the propeller. Propellers also affect the handling characteristics of aircraft on the ground, particularly during the takeoff run, when they produce effects that try to swing the aircraft to one side.